All right. Haha, not okay. So here's the thing. We've done a lot of work doing these 2D flows, these viscous flows, simplifying Navier-Stokes equations. You're doing it in your homework right now. Everyone's struggling and seemingly frustrated, but that's how stuff goes. Appreciate the difficulty of this Eulerian viewpoint of fluid field, of fluid equations. Right, if you remember back in the beginning of the term, right, we took the Eulerian view. Of the velocity field. So we go back, we drew some pictures and said, I'm going to draw a velocity field as some region of space where if you give me a point and a value of time, I'll tell you a vector of velocity going somewhere. And then from that, you get these momentum equations, this continuity equation to conserve mass, and then you have this system of partial differential equations. Pretty hard to solve, and that's something that maybe you appreciate when you're just trying to simplify them in any sort of problem you're dealing with, right? So this context, right, it gave us a system of PDEs we had to solve, which is fairly difficult. But if you make enough assumptions, you can get somewhere with it. So what we're going to do today is we're going to change our perspective, right? Where this was Eulerian, I want to go back and I want to show you sort of this, remember that Lagrangian viewpoint. Right? I just sort of threw that away in the beginning of this class, but we're going to revisit it because there are some things that are nicer about it. Right? And we can see those in maybe this in these two examples that almost seem like cheating to me when I find them and look them over. It just seems too simple, I think. I got to mute my Slack. All right, so we're doing Lagrangian's viewpoint with the path idea. Eulerian's hard. It has that system of PDEs. The other thing we're going to sort of address is this far field flow, right? A lot of times the analysis I had these arguments saying, well, that's really far away, right? Or we're beyond a viscous limit, right? And so think about far away in this 2D slot flow, right? Sort of we focused our attention on this section right here. And we said that this, right, was some dimension L. And it was very far away from the inlet of there. Okay? So if in reality there was some sort of fluid looking like this, right? And there were corners, et cetera, that we just ignored on the basis that this scale of the axial dimension was so large that all those effects had to be just combined in this epsilon term that we made to go to 0. And you sort of threw away this whole, right, this fluid converging in sort of dynamics. We just said it was far away. So something certainly should be sort of unsatisfactory about doing something like that. Always should be. We did it another time, too, right, in this Helmholtz flow or stagnation flow. Remember, this was this problem where it looked like this, right? And then this was our far field flow. It just looked like plug flow, constant flowing inward. But always we had some sort of dimension to say, well, I know what far is. So this was some sort of viscous length scale that you could get from the dimensions of your problem. So it's not totally arbitrary, but we say, well, past this point, the flow looks like plug flow, constant flow inward impinging on a plate. And you sort of just say that, unmotivated. Should be concerning. Even in the von Karman viscous pump, remember that crazy thing? Everything still was kind of based off this z-axis. Hope you can see this, right? And then again, right, in all this analysis, there was some viscous area that mattered, where we said past this point, I knew what the velocity field was. I gave you that it looked just like this constant flow inward. I did it again, too, even in early on when we talked about an ideal vortex. Or even when we did the matching example where we showed, like, well, far away it's 1 over r, but as r goes to 0, I have a singularity, so viscous forces must take over. But again, I did do this sort of trickery where if here's some sort of vortex like that and it's spinning around in a swirl motion like this, you know, we talked about viscous dominations going on right here, where if I get very, very low, sort of viscosity will end up mattering to slow it down to get to 0. And then again, though, I did sort of just say, well, the flow over here sort of looks like a far field radio flow, and you just sort of set it, right? Some circulation 2 pi r. And these are things, I mean, maybe it seems like everything I say in this class is unmotivated and you're completely lost, and I apologize for that, but you know, certainly these things where I don't even explain where they come from, you know, that always concerned me, for instance. This is even related to this concept of like some length away from a 0 point where viscosity matters. You know, in this vortice thing, if I just looked at concentric circles from above, looking down at the vortex, right, I would have concentric lines of increasing flow, right? Here's my r-axis. And this solution has this issue, right, where if I go in, it will just blow up to infinity. I mean, this is what this solution looks like. As I lower r, this velocity is going up and up into infinity. And that's not physical. Then we matched it, and we kind of made it, and then we matched it, we did something like that, where it goes down to 0, and has some sort of behavior like this, really. You can see that. So I'll take this away. And this was that matched asymptotic thing that we did, where we connected 2 solutions, where one had to obey no slip, and the other, far field 1, has a boundary condition we said looked like this. So our change of perspective is what's going to allow us to look at far field flows, and even simpler flows, such as something called an ideal flow. And really, I want you to appreciate that we're just now switching our viewpoint. Before it was Eulerian, where we wrote down systems of equations and tried to solve them by simplification, making it 2D. We're still doing the same thing here, but really our change of perspective is what motivates these next 2 lectures. If you just start from this, I want to go back to that Lagrangian thing and think about paths of fluids along think about fluid particles flowing along some sort of path. I think you would get all this stuff. So then there's sort of things about, well, I could sort of think it a good way to really measure far away. So far away is a length scale, and then there are ways to region that is far away. Right? So saying faraway fields. You know, at this point, you should have much greater appreciation for what this Reynolds number is that in undergrad maybe you just threw in a density, threw in a viscosity, and then threw some L in there, or even threw a velocity value that you knew in there. I mean, it really does govern a lot of things. Right? So this Reynolds number that comes about from a non-dimensionalization of our entire governing equations, right? If it's incompressible, I have some density here, some scale velocity, and then some length scale here. So this term governs a lot, right? I mean, it pops up in this system of equations. Right? So much of it came from here. Where does this thing show up? Well, in a non-dimensional form where I have a material derivative. So I'll explicitly say all this is non-dimensional. That's the negative pressure gradient. Okay, it pops up from just right, non-dimensionalizing, and you have a u squared over here, and then when you divide the entire equation by that, you would have a 1 over Reynolds right here. Or you could have it over here. I guess I should. Right, so this is what I mean by system of PDEs, because this really represents 3 equations. So now I have a u, a v, and a w, which all of these amount to. Getting a lot of questions on the pressure scale thing, so I will say what this form is, this is only if my pressure scales by this choice of pressure. Okay, so the Reynolds number is not attached now to this curvature term here because of the arbitrary choice of me picking, right, that my pressure will scale like rho u squared. You haven't heard it before. I like to think of this, right, as kinetic energy per unit, right, per unit volume. I think it's helpful to think of pressure as an energy per unit volume, just for reasoning about that. Right, so you have this form if you scale by this pressure. If you scale by a viscous pressure, right, then you could have the Reynolds 1 over Reynolds relationship popping out over here. If you take an average of them, right, you can get this form, which I do write to myself just because it's kind of general enough to prevent myself from making mistakes. Right? So I kind of do this trick. I feel I'm repeating myself on this stuff, but I understand it's not intuitive, right? Okay. So it would have this. So again, it's still this material derivative of the velocity side, but when I divide out all of my scale, right, this equation is true. Notice there's a difference of there's a 1 and now this 1 over Reynolds here. This equation is true, right, if I have my pressure scale as a rho squared and plus. Right? So this being, right, a kinetic energy per unit volume, and this being a viscous dissipation or work done by viscous forces per unit volume. Work is energy, so you can think of it that way too. Again, so you notice the form of the equation is changing based on the scale of how I choose to scale pressure. So this is frustrating, right? And you'll see later that this approach gets rid of the pressure. Pressure becomes a calculated thing after you solve what we're going to find. So maybe you'd actually appreciate this stuff coming up because it removes this pressure thing. You like it at first as a student, I think, because it's a little more, it ends up being a little more like algorithmic, and you just feel like you have the all-being power of a fluid analyst, and then you quickly realize it's pretty limited, and then you go back to this reasoning of the Eulerian view. Or you hate all of it, and you want to drop the class. Okay? Either way, though, you see that Reynolds is pretty important in here. What did Reynolds come from? Okay, the Reynolds comes from, right, these terms right here. Importantly, right, my rho, which is my density, right, fluid density, and my mu, right, those are medium properties, right? Medium, sort of the fluid. Right? They're fluid properties. They're really thermodynamic properties. Importantly, they don't change however you decide to think about your problem. Right? You pick a fluid, those things are set. You can't change that. And then, right? So then clearly the second things that we have control over in this expression, right, is my velocity scale and my length scale. So velocity scale is tricky because it comes from the initial condition of the Navier-Stokes equations, or a mixture of the initial condition, the boundary condition, or a scale of the problem itself. That's where your velocity scales have to come from to be consistent with your problems. But then there was this L thing as well, right? And L is related as well to the entire geometry of the problem that you have. Right? So again, what did we say? We said that these are sort of fixed, your density, they're medium properties, right? But these things, right, we have some control over them. And by control, I mean they vary by analysis. Right? They vary problem to problem. They certainly require some thought, which is difficult. Okay? But we did do some amount of work on where the L came from. And I posited and I showed that you could do a non-dimensional, and it comes from defining this non-dimensional gradient operator, right? So if you recall, I like to think of this non-dimensional gradient operator, right? If you were going to define this thing, or to find this gradient operator, right? You have this trace of this operator and then the non-dimensional part. What was the trace? If you remember that this trace thing is 1 over all of x, y, and z. Right? Where capital X, capital Y, and capital Z came from the geometry of your capital omega, or domain of flow. You can see this stuff. What I'm getting at is is this sort of trace right here. If you move right, is a length scale. It's a 1 over, right? It's this 1 over L relationship, which makes this non-dimensional. So in the non-dimensional case, though, it's about what happens to this non-dimensional gradient operator and what sticks around. And I want to show you, right, in the idea that we had this non-dimensional gradient operator had its own thing in front of it. Right, where are zeros here, and then these are similar along there. Right, this is a matrix where these are now non-dimensional epsilons, we call them, if things are very large. If one dimension clearly outbalances the other one, then you'd have these epsilons pop up from here. This is how you can imagine these coefficients. So again, we're focusing on an L right now, because I want to the idea being that when the length scales get very large, that things can even be a little more simple. Things can be simplified a bit more. So these expressions that pop up in here, right, they have these terms like this in the diagonals. All right, if x and y, if all the length scales grow very, very large, or of the same, of the same length, or if one, if these, or if these ones are much bigger, if all of them equally grow very much larger, then it would look like 1 and then 1, so it would be like a third, let's say. This is just a scale argument, but the idea being now, if everything blows up to infinity, if this one grows, well, those ratios don't really see a difference in that. You just get this, and then even still a non-dimensional. Operator. So the difference now being, when this x, y, and z blew up to infinity now, though, the non-dimensional gradient operator stuck around because of how it's defined. But the L is in the Reynolds, which is this parameter in terms of the equations. So all of these blowing up to infinity means this thing blows up to infinity, because the L is really 1 over that trace. And then what happens then is then this 1 over Reynolds blows up, and then you have this go, and now you're left with the material balancing the pressure. This is a case of ideal flows even, or irrotational flows. So it's another way that the viscosity terms won't end up mattering if you zoomed out far enough. So far field meaning like your length scales become so large that you don't really see any of the near wall effects of your flow. Again, it's measured by this L. So that's a way. So those are ways to measure far, right? You can think about the Reynolds view. You can think about how the length scale blows up very, very far for some sort of reasonable velocity, right? Again, L could grow very, very large in that scale, right? Right. You could have this, but then you could also have like the scale of the velocity go to 0. Maybe let's say faster, and the Reynolds number would go to 0 as well. That's one issue. But if you have some sort of bounded or normal, right, some sort of average velocity, then you could get this to blow up with just length scales. But playing around this combination of length and velocity scales, you can see more how you can turn on and turn off terms in the governing equation. A second thing of simplifications is this idea of irrotational flows. Right? Sometimes called ideal flows or potential flows. And we'll see why later they call them that. So, right, one natural, I'm just saying that one natural simplification you make of Navier-Stokes equations is you say that the Reynolds number is extremely large, right, meaning very, very fast, let's say, and that kills off these things, and you're left with a simpler set of equations, somewhat simpler. They're still nonlinear, but they have properties that end up being nice. But then there's another property of irrotational forces, which don't mean the viscosity is 0, right? It's just, right, effectively 0, right? So it doesn't mean that viscosity is actually 0 for irrotational flows, right? What irrotational flows mean is that, right, that viscosity has no effect, or it's effectively 0, right? It's that there's no imbalance of shear forces are happening in the flow. So the classic example that, right, you always go back to the concept of an irrotational flow is that of an ideal vortex, right? This is this type of flow that we looked at where here's the radial, right? So this is just flow that's spinning around. So it clearly seems rotational, but it's actually an irrotational flow. And the conclusion of it being really irrotational is sort of two things. There's a mathematical one, and then there's this idea of no imbalance in shear. Right? But this actually requires that you know what the velocity field is. But if I draw a little element, right, a little box of fluid on here, right, if it's ideal, it doesn't actually go towards the center. So that really means it's ideal because all vortices would actually have something go into the center. But this just spins around and around and around. And this box doesn't deform. Okay? The flow itself is quite rotational. It's just a spinny rotational flow, but it's actually this irrotational flow. It could be even a very viscous fluid, but if you have this type of a flow, right, if you have this type of flow where there's a vortice where the flow is moving into the board very quickly, it's still an irrotational, or viscous forces don't matter because there's no imbalance on the sides of these. Okay, if there's no imbalance on the side of these, one way to easily see that is look at the two tangential forces on this box going around for a spinny spin. So here's the center of mass of that. this idea of imbalance, well, viscous forces are talk about shear forces on little surfaces of on surfaces of elements, not the normal ones, right? This idea of viscous forces are talking about the shearing effects of the forces. So that gets you here. So no imbalance. There's no net force if I look at the shear forces. Right? And that's, if this is spinning at some sort of, right, angular velocity, omega or theta dot. I mean, if you remember physics 2, sometimes you called this a theta dot. I just use omega, but I also use omega for frequency. That's related because, angular velocities are, never mind. Right, so you have an angular, right, the idea you describe this, though, by an angular velocity. Okay, and then this velocity right here, the tangential one, right, it's going to be your r times the angular velocity. Or let's say an r1. Then this one right here, right, that's just the tangential velocity I have as I'm spinning around the circle. R times the omega. So this flow, however, though, is a 1 over r relationship. Sort of it's scaled, right? So this is over any r. So if these are r naughts and 1, because they're right at a point, these will cancel out. And this idea that there's no the shear forcing rate. Is this making sense? I should just quit on this one. I'm just saying that there's no net imbalance on here because a shear force is proportional, right, to a velocity gradient. But you still need to know the velocity field for this type of argument, though, which bugs me about it, actually. Yeah, the velocity here. I mean, certainly if this one's closer to the center of this vortices right here, it's spinning a bit faster. And the difference of this makes them even out. So there's no net imbalance, right? But this is the other better one, that an irrotational flow can be tested by this condition. The curl of the velocity field being 0 means it's an irrotational flow. So this is sort of a check. Given. If you give a velocity field, you can see that you can check to see if it's irrotational by this calculation right here. You can look up how to take a curl if you want. And this ends up having a nice property, because if you do have that situation, then you have an irrotational flow, and that means the viscous forces don't matter, and this makes it an ideal flow. So this is a nice check you do. Take the curl of this velocity field, and you get this concept of this ideal flow. Ideal flow not meaning that it's a completely inviscid flow. Inviscid flows are ideal, but irrotational flows do not mean that there is no viscosity force. And there's no viscosity in the fluid. It just means that there's no effect of the viscous forces. They balance each other out all the time. So I'm trying to just really get across the point that the irrotational flows don't mean that this. They don't imply this. They mean there's no net forces. There's no net shear imbalance forces to cause shearing or rotations. Boxes stay boxes, and they don't shear away and shear away. Right? The other classic example is if you just have fluid moving over a plate, right? Right, this very simple situation of a fluid flow where you just have a shearing top, a fluid moving across. There's no slip at the boundary. Okay, you have this linear flow right here. You do draw some sort of box here. There is some shear imbalance of shear forces. This velocity is faster than the bottom velocity, so there's a gradient of velocity, so there's an effective shear force happening. Right? So then if I go a little later, okay, so T naught and then T1, this idea that even this flow, which doesn't look rotational at all, right, is not an irrotational flow. There is some, right, there is a curl to it, and viscous forces have the shearing effects. So this would not obey this relationship, but the vortex flows the vortice flows do obey this. So even though, again, this doesn't look rotational, not an irrotational flow, even though it looks really flat. Okay, so now let's get into that path stuff. Okay, this path stuff we talked about. I'm thinking about velocity fields now as just these Lagrangian paths of fluid. And then let's even put a body sitting in some fluid medium. Some solid body. And we all see these things before, and they're really even motivated by these types of experiments where you establish some steady state flow field, and then you release a bunch of like bubbles at one end of the flow, and then you could see how they establish themselves around some sort of object. This idea of a streamline even comes, or paths of fluid, comes from just, right, a bunch of experiments of fluid flow where they would establish, right, some steady state flow around some body, and they would have like a wire right here, right? It would release like little bubbles of gas. And that way you could actually have some sort of visualization of how these paths establish themselves. So I'm just saying this idea of streamlines is just even a natural experimentation thing. And it's actually a great way to even check to see if analysis worked. And it ended up being a good situation. It ended up working. Okay, so you have the situation. Let's just call each of these ones different, right? So here's my one path, streamline 2, streamline 3, right, and a streamline 4. And there's a bunch of them, actually. Hopefully you already noticed that there could be like a continuum of these streamlines, just because I'm counting them out, right? There's one like infinitely close to this one as well. But just for rationale, right, we'll just break it up into 4 streamlines around this body, and I'll call this one, and then this one. What do we have next? So in this situation, you still have to define your coordinate system. So that's my coordinate system, right? We'll go Cartesian on something like this. There's a body. Don't forget, we could also think of this stagnation flow. Okay? So remember, we had stagnation flow where flow moves in. It's kind of like that impinging flow problem we did in the advanced lecture, right? But then even draw this streamline where there's an impinging flow where I hit the body and I immediately stop, or the stagnation point. And then even around the body, we'll have things like this. And then like in airfoils, you actually can have, there's stagnation, a point being where the flow comes in and decelerates all the way down to 0. There's even actually stagnation points on the end of a body, right, where it's seemingly they emanate from 0 and immediately accelerate forward. Multiple stagnation points maybe you haven't seen before. So this is the viewpoint we're taking right now of just thinking about the fluid flow. Right? think about these paths the particles go along, right? This idea, if I set up some sort of gas bubble right here, right? If I initially place it right there, it just travels along some sort of defined path. Maybe it shears, maybe it doesn't shear. But this is the image that we're having, right? These are little surfaces of fluid. They just move along this one path in the steady state scenario. Oops, excuse me. So then what is this S1? Right? All I've said is I'm going to imagine the velocity field really as being comprised of just a bunch of paths of fluid. That if I release something from there, they just travel along their little paths, right, unoccupied. So then really this description now of what the path is, these S1s or S2, is something we have to accomplish, right? So any sort of path in xy, you have to think of it as some parameterization, right? So here's an x1. It's something like this, right? And you can play around in like any sort of graphing software to really see how this stuff works. I mean, you can write any types of functions, but the idea is if you have x and y parameterized by some a, then you get these curves in the space, right? If you can't remember, right, just think about how you write the equation. Right? Think about how you write the equation of a circle, right? You're in an xy plane, and you just type this in, and then all these points x and y that satisfy this relationship draw out a circle for you. Right? This is still my x and y plane, but just the idea that if you're defining some path of fluid, right, some path or some curve in xy space, this is the general form you have. Constant could be 0, could be not, but you leave the constant there because you can define many of these things the same way. Right? Think about it as if I have this. Right? If you have multiples, right? These describe two different circles. Right? Same idea of this general idea that there's some function on this side that's a function of just x and y, the coordinates in the space, equaling some constants, is how you define this path in two-dimensional space. So that's a general way of how we could actually define these things. So the other thing maybe you should say, right, is I've already made some assumptions on the fluid, right? What are they? Right? The idea is I've already made the 2D assumptions. I already said flow is 2D. I've also said steady flow. So I already made assumptions on what the flow, what the behavior of the flow looks like, where there's no unsteady effects. And I've said it's established some sort of constant, right? Established some sort of constant distribution of flow, right? So I've said 2D, I said steady, and that's for an ease of maybe describing what the stuff is about. You don't have to do this with this interpretation, actually. There's a much more complicated formulation of this idea where it's totally actually in three-dimensional space and it can be unsteady. I'll show you 2D unsteady, but just realize I'm only doing the 2D unsteady to just quickly get along to how this path stuff gives you a different calculus of getting your velocity fields. Okay. So these are paths of fluids where they go along at some speed. So the path has information about velocity in it, right? Because as I've just defined them, I said this is some sort of path, and the fluid goes along this path. Right? So the path has information about velocity in it. Right? If we look at just some part of a path, right? Here's the point right there. Here's my coordinate system, right? It's going at some velocity, right? So to get to the next point, a curve can just be broken up into little tinier and tinier triangles, right? It had to move some distance x and some distance y. That's fair to say, right? So it goes some sort of dx, and that dx would be, this is not big enough for you to see. Right, so what matters is for this streamline 1, for a point to get from one point to another, it has to go a little bit in the x and go a little bit in the y. And since it's moving at some velocity speed, we can claim that the velocity is what does that. So if I zoom in here, where this is just zooming into this very top of this triangle to approximate, but infinitesimally it gets better and better, this approximation. So we get from point 1 to point 2. Okay, so it's moving at a velocity, right? A little change in distance is going to be what? It's a kinematic relationship, right? That a little bit of change in the x dimension had to come from velocity times a little bit of the time. And then a little change in y had to be the velocity in the y direction times the same amount of time, right? So I can't measure time differently in these two to get this triangle. So it's actually pretty important that these dt's are the same dt. That this dt is not some different, right? This isn't 5 seconds, this isn't 1 second. That they're the same. But a dx is from the relationship of velocity times this, and that's how the units, and right, even look at the units, that's how it works out as well. So we're getting closer to something. That I have paths, I have a way to define my path by this equation right here, right? It's just my general sort of description of a path, and I'm just focusing even on one of these things, even an arbitrary constant. But I want to sort of motivate this sort of seemingly strange relationship. Oh, it sort of bugged me. OK, so now let's look at then a little change in that path. So ds1, so a total change of this function. Again, this function s, I've said, is what's defining these Lagrangian paths. I don't know what they are. I'm just saying fluid velocity fields, steady, are defined by a bunch of curves in space. And that's as general as I can make that. And then this is the other thing where if I'm on some point in the path and I move a little bit further, I have this kinematic relationship that I claim. So function-wise, we have this. Now what's that? A little bit of change in s. This is equal to a constant for all points of x and y. Again, if you're unclear about these circle paths, right, about these paths, just think about the equation that you write for a circle. Right? If this is going to be r, and I'm on my path here, and I'm looking at, like, well, what's this change here? So this being a 0.1, and this will be my 0.2 for this. Imagine it is moving around there. Right, so the equation of this circle, right, I just have this. So here's r, my moving 0.1 to 0.2. Right, so the change of, right, these changes amount to nothing because this is going to be a constant. Right, there's no change happening between this point and this point because they're both equal to r2, right, to r squared. So it's really the same idea right here, right? Where in this case, I know this equals 0 because of just how I've defined or parameterized my path. Yes, of these points in x and y space, they equal to some constant I don't know what it is, but that's how I'm defining my s1. And my s2 would have a different a, etc. So the change in there has to be 0. But you relate that to by actually taking the derivatives of this side, right? You could also think about taking the derivative of this equation, right? So you take a total derivative here and then a d dA, right? So change of a is 0, and then I have to take this derivative here. Or a total change is what you have to do with this. So at this point, maybe I hope that you Okay, and that's just this is just a calculation you do from the properties of multivariable calculus. Okay, so this is a property of multivariable calculus of how you would actually take this total change. Right. One other way you could think about doing this is if you were to say sort of, what is ds dt? ds dt is a dA dt, which is equal to 0, right? But it's also equal to, right, okay, and this is applying the chain rule to a multivariable function. But this top d, all it's doing is just not caring about this dt right here, because it appears the same in all of them. But you can still think about this way. Okay, importantly, though, it's that you have this is equal to 0, right? And it's equal to 0 based on a sort of just the pure definition of how I'm defining a path in 2D space. So now I get actually a relationship for what the tangents are. Right? So from here, you get this. This is important just if you go back to here, right? Because this gives some identification then of what these are. So there's many ways to think about this. Some people define stream functions as like the tangents of this and then equaling this. But you also think about just look at the definition itself in this triangle you get, take the derivative with respect to time, do your chain rules and multivariable calculations. You get this relationship that this dy dx has to be equal to this. I get a negative sign because of this 0 relationship. I have this dy dx because I move one side over the other, then solve for a dy dx, and I get right here. But then the kinematic relationship, seeing a dy dx, I see that had to be the that has to be the v velocity. This has to be the u velocity. So I get this identification of top and bottom. Right? And this is really critical. These are sort of fundamental. To how everything goes. And it's really important, that minus sign. It seems, it's amazing the structure that comes about because of this negative sign that appears in there. But it really is everything. So these are just S1s. This is just me doing it for one path. One path I have, right? Now, what you then do, I think, is then you say, well, that's just if it equaled one arbitrary constant A. If I had any other A, it's a different path. Right? So I could just have it be some function, right, equaling some sort of constant value, but that constant value could be a continuum of numbers. So it's infinitely changeable. And that's where you kind of shift this focus of there's some sort of stream function that I could suppose, right, where A just can vary for any sort of constant I want it to. Right? So while this initial approach is me just focusing in on one path I've defined, you get this relationship and you have to stop and go, oh, wait a minute, since A was arbitrary, right, this could represent some sort of function just equaling a constant value. And the constant value is what you don't know. So alternatively, you don't know what A is, and you didn't know what S1 was. So then you call it phi, right? I don't know this function, but I'm saying there's some function up there that defines all of my paths. There's some function, right, psi, where if you give me any constant in front of it, I will give you the path. And I'll give you the right, I will give you the path function. And if I knew this function, I can then calculate velocities from it. Okay? This is important. These are critical equations, and the idea is it's really a special type of potential function. The idea being, I find one function gives you u and v. Again, we're in 2D and steady right now, and that's because that's only to make this simpler to rationalize. But you can do this in 3 dimensions. And I reference any of the textbooks I've assigned. They have this segment where they go into the 3-dimensional case of these stream functions. It's trickier, though, because if it's in 3 dimensions, instead of parameterizing these lines, you have to parameterize these paths as the intersections of 2 surfaces in 3-dimensional space. So you can imagine how much more complicated that gets, but we won't do any actually 3D stream function stuff because it's quickest and easiest in 2 dimensions. But these are almost like the Navier-Stokes equations for stream functions. They're very important, and the negative sign is extremely important as well. Again, the negative sign coming from many rationale. But I think the negative sign is extremely important, and it comes from the idea that when you took this derivative, you had a 0, so you move something to the other side, and then you have this negative. From a definition of how you're describing your path in the most general sense. Okay, so we'll keep that there. One other thing, though, and that's where this breaks down. Right? Because this argument breaks down if you have stagnation points. Notice right here, I can't take a tangent there. Right? This curve here, I'm going to erase this right here. If I look at that body curve, right, or this stagnation point, it looks now like, if I just thought of that 1, right, I have kinks in there. Let's call this my S0. So this is an issue, right, because I can't do that same tangent argument with a dy over the dx. So one way to interpret that then is this becomes undefined right there, or really that you have the velocity equaling 0. If it's 3-dimensional, what happens is it gets to here, there's 0, and then there's a separate part, and then it goes back onto here. So if it's 3 dimensions, what's happening is you stagnate, and then let's say there's no defined direction after that stagnation point. At all the other ones, I have some defined direction to go in a little bit later. But once I hit this stagnation point, right, I have an undefined tangent right there. So even in a 3-dimensional case, what happens is it turns into a bunch of different directions spreading over the body. But you have this is the idea that in these path functions, it's a condition that you have to have stagnation points have 0 velocity. They're undefined. It also makes sense that it stagnates, But it is sort of strange. I mean, the idea of like, do you really think a stagnation point exists? I mean, like, it's, you can, if the particles are big enough, they might just bounce around there, but they're certainly unstable. So they are sort of like this Platonic idealization of the real world, I think. So now let's think about this, right? This is the idea of I have a u and v now defined by this psi function, psi, right? So one way you think about this now is my velocity vector, which is a u and a v. I have now some new relationship I can quote using it, right? Where I have some now special type of derivative operator now that looks like this. And it's a column vector. I want my vectors to be column vectors. This is a scalar number, so you can scale a column vector, and then this operation is well defined. So this now, right, this is going to be my velocity in terms of this interpretation of streams, right? Different from the other interpretation, what did we have before? Before we used this gradient operator, right? Trying to point out that there's something going on with this derivative, because this pops up in the Eulerlian sense a lot, your gradient operator, and then twice of it, you get matrices, you get diagonal matrices, etc. But this one's different. This isn't even a row now. This is a column vector, and it has this negative sign hanging out in there. So one immediate property of this is it already satisfies continuity. Okay, continuity is, right, this. Does it satisfy this? And it ends up that it does, right? And we can see that if we just compute this. So I'll call this, sorry, I'm going to call this a gradient dagger. So I'm just saying this thing right here that's a column, I'll define as this gradient dagger. So then for continuity, right, this dotted with dagger all right, the scalar number, so I can pull that all out. And then this computation yields what? Well, you can do it, right? This computation would yield right, this dotted with right, so I have a row and this, but I can dot these two of these vectors. So you get the same, and then adding them both, you get this negative, so you get this. So it satisfies continuity, right? If u and v are defined this way, with this operator, then this will be 0 for any v. Interesting, right? So for free, you automatically satisfy one of the equations of Navier-Stokes. We automatically satisfied continuity by thinking about this stream function and the paths that particles go in. Okay. Importantly, what happens is you get this relationship, right? This is the zero operator. It just takes any function and makes it 0. Tricky, maybe sort of situation happening right here is really you need a condition that you can mix the partial derivatives. That, right? The idea that, I mean, in reality, this calculation ends up being this, where I have this swap of order of taking derivatives. You need to be able to swap this, and that's a statement on like I have a smooth function. I have some continuous smooth function. So whatever my psi function or stream function I'm looking for, if it's nice and smooth and continuous enough, then I am ready to swap these derivatives. Is it true for turbulence? Do we believe the stream functions of turbulence are smooth? I don't look at that experimentally. But do we believe, but maybe it could be an issue of our measurement devices that we get random fluctuations in our that seem as if they have kinks everywhere, and you couldn't do this. But you do see stream functions a lot. So there could be an idealization of some average type of flow thing, and then it could be smooth enough. Or it could even mean, or this could even true. The fact being that we just can't zoom in close enough to actually get the smoothness, curvature of what's happening in that flow. But the idea, just thinking about that. Okay. Almost done with this development stuff. And again, I do this so you can, whenever you see these stream functions or psi functions, that you know exactly what goes into them. Right? So if you're anywhere and you see someone using a stream function, you know where it came from. It's coming from this idea that you're describing fluid paths, not a vector field. Right? And the next thing is, since continuity was already satisfied by the definitions of the psi, of the u and the v, next would be then the momentum equations. Okay, so momentum equations, right? Well, momentum equations, we have this. I'll do them dimensionally. And I have a, once you appreciate this interplay, okay, I'm doing this dimensionally for you. So here's the momentum equations that we have. In this framework, I've automatically satisfied continuity. So now I'll transform this to talk about now not be a statement of my vector field, but a statement of my potential function, psi. Right? Again, you see the power, really the power of psi is if I knew what psi was, I could calculate u, I could calculate v. One other thing, right? If you know what u and v are, right? Since if you know what the vector, if you know what this velocity vector is, based on psi, then you can calculate what the pressure is. So we're flipping it, right? So one way, right? So if I want an equation now to get just what psi is, I want to get rid of this pressure term. And then it would be an afterthought to any sort of analysis using a stream function. This is where questions would arise if here's a real classroom, but I'm sorry no one is here. But let's iterate that again, right? I say this better, right? It's such a swap. If you know what psi is, you can calculate u, you can calculate v. Essentially, if you know what psi is, you know what the v vector is, right? And then you could just really move this around, right? So say, right? Say we know psi, right? X, y. Well, if I know that, okay, I can get the velocity vector just by doing this, dagger gradient operator thing I've defined by the function. So it's a scalar multiplication by some column vector, well-defined. So then I can get what the velocity vector is. Then I could do things right here, and I could calculate pressure, right? So I know what this is. So then you could just sub it into here. I mean, then explicitly we could just say, oh, I could figure out what. Right? Moving everything to one side. It's steady, right? So we'll just say steady. Again, you don't have to even say it's steady. This still works for unsteady. So for our situation, it's unsteady, so this is gone. But again, appreciate that I know what this velocity vector is. I know what that is. I know what that is. I know what this is. Viscosity, right? So then it's just a matter of then I could calculate the gradient of the pressure, right? You could even say then that the pressure then is so much an afterthought that ends up just being a rho, and then it's an integration process you would do. move this over, get rid of this gradient operator by doing an integration over the dx, the dy, and the dz. Again, stressing the fact that if we can eliminate the pressure term from this equation, that would mean that it would be then an afterthought. And really, that's still the same case with our momentum equations, too. Again, realize for incompressible flow, the same thing's happening. So how do I eliminate pressure of this term? How do I eliminate the pressure of that term? Well, we already figured out how I can zero something out, right? This, I know, is 0. Right? The dot product of my gradient operator and my dagger operator gives me the 0 thing. Right? So that's this situation where I then go, I'll dot this then with my dagger operator. Right? I do essentially in the notes what's happening is I say, take the y derivative with this and take the x derivative with this and then subtract the two equations. Seems like it seems less like you would know what to do to me instead of actually just going, it seems like my u and v are defined by this new differential operator here. Well, I see by continuity that this operator zeroes out. Well, I see I want to get rid of pressure, so I can just dot this whole equation out by pressure, and I can eliminate the pressure term and get a new equation for my velocity. Essentially, I'm deriving now the psi ODE, PDE. So then it just ends up being a process of calculating out some terms, right? So, right, we already said that this velocity vector is this v dagger psi. So I'd substitute that in for all of these v terms. I know that this goes away once I dot it with here, right, because this is 0, so that gets rid of the pressure term. There's a vorticity interpretation as well that we'll get to later, because I want to wait for vorticity. So right, dotting this through, dot and then dot here, that would go away. And now I'm left with just some other calculations to do. I guess I have to do it on this side. I'm sorry. Do I do this for you? I really want you guys to start doing these calculations. I want you guys to start doing these calculations. Nope, I'm not going to do it. I'm going to do it. By either the form of the notes where I say take a dy, take a dx, subtract the two equations from each other, or this interpretation of this operator that I now defined, you then get the new momentum equation. You get the PDE for psi. Okay? Ends up being this t Okay. Either way, hope someone does it. Right here is sort of the new PDE that now governs what this stream function is. You back up all the reasonings, it's impressive where it just comes from, but this is the bad boy you got to solve. If it's steady state, actually, we already said steady state, but you could have a time part in there, right? Essentially, you could have psi of x, y, and then t, and this term would then stick around. You get these things from the convective part. Here's the viscous part. So you already see now you can have a stream function for viscous fluid flow, right? If it's inviscid, this would go away. But it can stick around for viscous flows as well. That's this term right here. This term right here is going to be your convective term. Here's that unsteady term. Right? You're just really rewriting the same equation a different way. Okay. Only thing that happened is I dropped the pressure out of the term. So there's another interpretation we'll see where if you write Navier-Stokes equation in terms of vorticity, then there's no pressure as well in that equation. Then this stuff might be a little more natural. But I want to spend a whole lecture later talking about what the heck vorticity is and why people use it so much. OK, so here's your new Lagrangian governing equation. Properties of it that are nice, right, is it's 1 PDE. Not a system anymore. Right? I mean, it's 2 variables. Right? For 2 variables, it's just this is going to be this. This is for 2D, right? If it was 3D, there's more of these terms. You can even guess what they actually are, besides this term right here. So it's 1 PDE, not system. Kind of cons is it's 4th order. Not the best thing. So we traded difficulty of having a 2nd order PDE with now having a 4th order PDE, but we've traded complexity. Now, if I solve the Lagrangian viewpoint for paths, I can find one function, a potential function, governed by this. It automatically satisfies continuity. If I find psi, I can take derivatives of it, get my velocities, uv, and then I can calculate pressures afterwards, because it's removed from there. It's a scalar function, too. The other thing that I want to stress about this strange thing of this psi, right, is you can just define any psi. Right? By just writing down anything that pops into your head about a psi, x equaling y. Any sort of psi. You could still do this process. Where before you had to do a lot to even figure out what type of flow is happening. Here, you just write down a psi, some sort of crazy function with x's and y's. Then you go ahead and just see what on heck would those velocities be. And with those velocities, you plot them and you see what kind of flow you're modeling. That is a very tricky thing. But it makes it a lot easier. This is stream functions, right? Stream functions flip everything that we've been doing. Another thing, what are the units of psi? Right? You can see we've gone through and looked at what this psi function is, but what are the units of it, right? I mean, it's not that hard to do, right? If you have just take one of these equations, right? Okay, so this is right. This has length over time. This is length over right. Not time. This over an L. Okay. So now you know what now what the units of psi are, right? Those are the units of psi. Your stream function, right, has units of length squared divided by time. So another way, sometimes you can think about this as I could also think of psi having units of a flow rate, which would be length squared divided by time, and then divided by some length. There's another interpretation of how you can think of this. That's another way you can think about what the stream function is, right? This stream function phi is actually a flow rate divided by some length dimension. Actually, in and out of the board is what it really is, right? Some in and out of the board term. Or length squared. Those are units of psi. I'll test you on that. I have some summary, too, of what you really need to would get that idea. Most importantly, though, the idea is this. Started from Lagrangian, talked about paths, took derivatives and tangents of paths, came up with some different system of describing velocities of u and v. So the most important benefit of this stuff is that, just that. You get a new way to calculate u's and v's, all based on a psi function. It's called a potential function. Okay, so does it make your life easier? And I argue that, right, in some cases it does. And this is a viscous case. Right, so let's do this situation of a suction flow. So here's y, here's x. Okay, so let's have some sort of porous top and then porous bottom in this model we're going to have. So sort of. So these are porous walls in this flow. It's a 2D slot flow. Or you could think of it as a radial flow of concentric radial surfaces, right? Concentric radial surfaces where this is an interior radius, this is the exterior radius, and you're just looking at like really large veins. Here's some, and then there's some diffusion that's happening. So when I mean like suction flow, I mean there's some pressure gradient actually in the y direction, right? So there's actually some amount of osmosis, I like to think of it as, that's sifting through this flow. Okay. And maybe you remember when we did all of the 2D slot flow totally non-dimensionally, there was an extra term that stuck around. Right? There was an extra term stuck around that had this V. Right? And we know that V star was equal to some constant value. And then what you then said was that constant value is equal to 0. And then that term went away. What if it wasn't equal to 0? What if there's actually some small amount of velocity right here that's due to this cross suction happening in the flow? Keep in mind, this is a very, very simple model, but helpful model to understand like if this is blood even, right? And these are vein walls. You could have some type of osmosis pressure happening, where there's some cross-pressure gradient due to like the osmosis happening in your blood veins to some amount of organ in there, where it's drawing nutrients, et cetera, away through the porous membrane medium, through the porous walls. Essentially, with this concept, you need the wall to be stiff enough that it can be assumed to be stiff, but be permeable enough. So that's the concept for this flow that we're going to look at. Okay. So it's 2D slot. Okay. Understand 2D slot flow enough, right? This is the same idea as having, let's say, my z-scale go up to infinity. If you non-dimensionalize, you would say, OK, 2D is what we're going to go with. So I have 2D slot flow. We'll say steady, right? Just because. Right? Steady is a weird thing because you can always say unsteady or just steady, but like steady is so important because like, right, unsteady is talking about like responses to forces in the walls, let's say. But after those have died out due to viscous forces, the flow is then steady with its viscous forces present. So the idea is like unsteady flow is modeled like where this idea, I hope you remember, right, is oscillating pressure, these oscillating plates, etc. We're looking at this like response of fluid to some immediate motion. But steady is always a good one to start with just because like you don't really care about that impulse reaction of what the flow is doing. You only care about like what the flow field looks like once everything's been established. You have like nice steady flowing liquid, as they call it. But so we go then steady on this. What other assumptions were important for the 2D slot flow? Right? Well, the other one was being fully developed. Right? Fully developed meaning, right, the other way, think of this, if this is the x thing, you could have that going enough to infinity where that essentially in the scale sense, what that is telling you, or fully developed could be thought of as like, well, the entrance and the exit of this slot are just infinitely far away in terms of the scale I have. So again, scale argument, or you just say it like, or you just say it. So those are important to have, right, to have this system be written down. Now, what I'm not going to do is I'm not going to write down those Eulerian. I'm not going to write down the Eulerian right, and the Eulerian system, right? What else is here? From continuity as well, right? Sort of importantly, this analysis does say if you conclude from the continuity momentum where you have all functions of x, all functions of a on one side, you have that this axial pressure gradient has to be equal to some sort of constant. Okay. This conclusion you have that there's a constant pressure gradient in the axial direction. That's really everything we need right now. Okay. So now let's think about this problem, and we'll have some h as well. Slot thickness. So everyone's frustrated about non-dimensional. So then now let's think then about these problems, right? So what are my scales that I want to involve myself with for this type of a problem? Okay, well, so then I'll have my u. That's going to scale as this like u, right? U. Let's not do infinity. It kind of means far field, right? We'll just say u naught. U naught. What are the scales I picked right here? Velocity. What should the v1 scale like? Well, you only had one, right? There's a boundary condition on the v, so that's going to scale like this v naught as well. At this stage, you might not know what the u naught is, but I'm saying when you do the scale stuff, you draw these pictures and go like, okay, I'll scale like that. This v will scale like this. What else do we have? Average. I don't really need to do that. I did this one. I don't know why I said that. X height. Right here. So these are saying I'm actually only going to zoom into like let's say an H section and then a H and a Y section of H and then look only at a H section of the flow itself. So while fully developed is satisfied in this idea, it's a situation where I have a velocity constant here and then constant here, and I'm just going to look at an H-size section. Okay, your Reynolds number. Right? Remember, this is a kinetic velocity. Okay, then what was, now think about this stream function, right? What were the units on it? The units on it were a velocity, were L squared divided by t, so that's the same thing as a u naught times an h. Other things we have, a v naught. This is this scale, right? This dimensional velocity scale right here. I'll say this looks like that. So notice my u and v are scaled by the same velocity. All velocities are scaled by sort of like this, right? This v naught. Sorry. That's what this is saying. I'll scale this by u naught, this by u naught, and even this by u naught. All right. So then the other scales I defined a parameter that pops up as well. There's this parameter as well. I'm calling it an alpha. Okay, and that pops up from doing this stuff. But again, sort of think this means then that my non-dimensional velocity is a u divided by a u naught. Non-dimensional v velocity is now the v, which I don't know, but I've normalized by the same scale. And even now my non-dimensional boundary condition for this porous flow suction happening is the initial condition still normalized by this term right here. other scales I have? These are just defining everything to be non-dimensional. Okay. So that's what we have situation right now. Now we need to come up with some sort of gauge or some guess now of what the stream function looks like. Time? Use the scales I'll have for later. So now, if in terms of, like, again, we're looking now for I'm not looking for the functions of u and v, but these scales will come up later. But really, this whole problem is just saying I'm looking now for this type of problem. I'm looking for this psi function, which you could non-dimensionalize using the x's and y's. And I'm going to just use this equation. So one thing to do always is this idea of a gauge. So stream functions, there's a couple ways to think of it about this, where you have this, let's say, coordinate system right here, where here's an x and here's a y in this flow. Just going to draw it here when I'm running out of space. So here's the y, and here's the x, right? So this point is 0 and 0. So then for my stream function, right, there's just points, right? The stream function is just defined by this domain, and any point in there gives me a scalar value for the stream function. So this point's 0, 0, and this point's x, y. So some point in the field, I'll call this just an arbitrary x, y point. Right? So then it doesn't really matter what I do. I draw some point, I could draw any sort of path from this point 0 to this point x, y. And you could ask what the flow rate through that, you could ask what the flow rate through that path is. Let's say, what's the flow rate going through this line that I have? It's also just you have this gauge idea where, since the stream functions are always defined in terms of derivatives, maybe you notice this, right? So if u and v, right? So u is equal to some derivative term, right? So I could have, right, you could have a psi function right, plus any point, right, or minus for that matter, which is what we do right here. And then the derivative wouldn't care about this because it's just a number. A function with two actual inputs just outputs some number, a constant value. So if I take the derivative, the velocity didn't care about this gauge happening right here. So sort of 0, 0 is an arbitrary choice that you make. But it makes things better, but it does make things easier. I guess I like to just think of this, though, as just, well, what is this x, y? So this idea of then looking at this gauge, or the idea of looking at what the flow rate through a path is, what does this equal? Ends up equaling this. This is a constant value. V naught is constant because the pressure gradient is constant. And then the u is what we're trying to look for. We know u is not a function of x because of the fully developed thing that we're speaking of, right? So not saying, right, u is not a function of x. So this u is not a function. U not being a function of f means this, right? So this ends up being right. So where does this idea come from? If you look at what is the flow rate occurring through this path I draw, using the definitions of this in a triangle, You show that it's just the points. That makes sense. I mean, this is just right. This is just the definition of. I mean, this is really just the definition of taking like the integral over a surface of your vector field, right? The idea is just being these 2 points. How else could you say this, right? Minus extra credit, but everyone's a little confused, right? So, right, you have this right here. Okay, so you have this deciding theta. What did you get there? So just integrating this, right, you would have this evaluate at the boundaries, which is the difference, and then you have the integrations happening here. Don't know. Important part's this, though, right? I have this gauge. I'm going from psi naught, or 0, 0 point, up to an arbitrary xy point. So if I figured out, right, if you solve what this form is, then you could figure out all of the points in xy. But the idea is having this difference or gauge allows you to look at then this term, where this is a v naught times an x, and then I'm just looking now for this fy. Notice if I have the fy function, then I can figure out all of psi. Move to the other side, right? I now have a form, a functional form of what psi xy is, right? Arbitrarily, though, I could have just done any sort of difference of points, but the difference being I know better. I know what this fy is. So just I have this. If any, there's a derivative of every term of this major equation. So this is never going to pop back up. There is an x, so things will pop up as well. And then we just go ahead and do it, right? So if I say unsteady, this whole term is out. If I say steady, this whole term's out. And then you just run through and plug in everything you have. And then you plug in these non-dimensional terms, which I've defined everywhere. And you get a very, it's not very simple, but then you just get this. Get this equation. ODE for the f of y, fourth order, and it's linear. Didn't do this part for you. Show that the alpha pops up right here after you just plug it into this thing. Everything, right, is actually doing the non-dimensionalization, just subbing these things into these expressions and what they mean. Also, this term here, I have in the notes, this to the fourth means this. So I have the set, right? It's a Laplacian squared. So what you end up getting is 4 of these guys plus 2 of the cross, and then 4, and then 4 of the y's. Well, right, you'll see that this, right, the y's don't matter because they just have the 1x there. And this is your governing differential equation for the ODE. It seems, I mean, it really does seem sort of like circular and like I'm cheating on this stuff, right? Because I had another governing equation which is fairly easy to like reason out what it was, and all I did was I just plugged in the stream function argument in here. So everything fell from this form right here of the psi of any point xy equaling the flow rate through it. That ends up being this negative v naught x, and this y term right in there. When you guys see that this difference, I have this. All I'm writing here is this, right? We're an integration, integrate the psi, and these have definitions in them. Get this ODE. Get this. This is the solution you're looking for in terms of f. Now, you can do this by hand, or you can plug it in Mathematica. If you were to do it by hand, the way you would do this is you would make a substitution saying, well, I'll call, let's say, lowercase f. I'll call that f triple prime. You sub that in there, and this becomes a first-order ODE, which has a formula for it in terms of an integrating factor. So you can just write out the solution there, and then you can just figure out what f is by doing 3 integrations of that. So that's how you do it by hand. Not going to do it by hand. You can look it up so we can get around to it, right? So this ends up being, in a non-dimensional case, some constant cubed boom. And then I get what the f is. More importantly, I also have made a definition of what this constant value is. And I've done that to make the math look pretty, so it's more easily interpretable. So here is asymptotic section flow. Okay, define this constant to look like this now. It's a beautiful equation, right? And then if you do some plotting of what this looks like, you'll see that everything's a function of what that alpha was. Now, what is the alpha? Right? We define then this alpha like this. This is equal to this porous flow, then a height divided by dynamic viscosity, right? So this one parameter alpha has an interpretation, right? Right? It's a ratio of this porous flow velocity that's seeping through the slot, right, over your viscous diffusion velocity, right? That's what this is defined as. If you take this mu and divide by an h, you're getting a velocity value. It ends up being the viscous diffusion velocity, or the speed at which viscous forces are diffusing through the flow itself. Importantly, though, that alpha is this measure, right? If alpha is very, very large, it means that it's mostly actually just this porous flow seeping through. I don't even see the effects of the actual shear forces or the flow happening at all in here. I don't even see a velocity gradient. But if the viscous forces are the most, viscous diffusion forces are the most present, I don't really see any of the alpha, and it just basically will end up looking like this. So if you plot that solution, what you end up getting are these curves based only on alpha, right? Where I have one looking like this, right? Where this is alpha equaling 0. And then because of how I've defined direction, here, where it's still no slip, it looks like that. So you see, sort of as there's more and more porous suction happening in flow, there's more of this pressure that's shifting that velocity gradient towards the actual other end of it. If there's none, I just get back the regular slot flow solution that we had before. And all of that does come up from just looking at these terms that you have right here. I mean, certainly the C naught, if you look at that, if you look at this alpha becoming very small or large, you'll recover all of the same analysis we did before. The other trick that you can do is you then do this calculation of pressure. So let's see that in action, right? Right, I told you when we developed this idea of the theory that if I had the psi, I could then calculate out what the pressure gradient is. So let's do that, right? If I have this dp, so being this, just calculate that out, and then I have this C naught divided by alpha, right? So this is now right, now I can calculate what this pressure gradient is. And this comes down to, right, for the same flow rate, right, and a scale velocity, what's the pressure gradient that results from it? So there's a flip that happens in the stream function where you're asking to calculate out a pressure gradient. You say, well, to get the pressure gradient at a constant flow rate and some sort of alpha, what would satisfy that to give me my pressure gradient? Understand that sort of difference of what we've done, where we said for the exact same velocity that I have. Everything was scaled by the u naught in that term, right? If you go back, right, the idea that we had a u, I scaled everything by one velocity. Right? There's no competing velocity scales in this type of problem. So this interpretation of calculating out the pressure gradient is just saying that. Right? For some flow rate, if I keep the flow rate constant, what's the pressure gradient result if I have an alpha? Slightly different. This stuff is slightly different because of this swap of this swap of what's important and what's not. Okay. Next is irrotational. So now that's the idea that a stream function can be used to solve a viscous problem. If you think about flow rate from x naught, and then you just plug that stream function then into that new governing equation, and it just certainly seems easier. I mean, I just had one equation. So many things drop out just from looking at what derivatives are constant. So now let's do this irrotational flow. Right? So irrotational flows, right, are sometimes called an inviscid flow, a potential flow, ideal flow, almost interchangeable words, but they're all talking about the same thing. And that is this one conclusion, right, where if this is satisfied, then you can say that the velocity is equal to the gradient of a potential function. So this is not the stream function definition. Okay? Notice this is the gradient. There's no fancy conjugate gradient operator that I've defined. This is the gradient. So if this is a scalar term right here, right, what this is saying, right, is that this idea says that I can get the u velocity and I can get the v velocity similar, right? So importantly, remember that when it comes to irrotational flows and potential flows, this is the difference, right? No swap, no negative. It's just straight up, right? So phi with x gives you u. Phi with y gives you v. I will test you on that, the difference of the stream function and a potential function, right? The stream function is special because of that, right, negative sign and the swap of the derivatives. It's special because of that, because that type of formulation automatically satisfies continuity. So you throw away one equation because it's already solved. So this is called your potential function. They're very popular for all types of fields: physics, electromagnetism, magnetics, quantum mechanics, everything uses this idea of potential functions where I'm trying to get some vector valued thing, so I just think of a scalar valued thing, take derivatives of it to give me everything I want. So again, this has a different interpretation, right? If I plug now this into continuity, you get for an irrotational, inviscid, whatever you want to call it, right? Now you get this property, right? I've just made this definition swap where I put the v, it's the gradient of phi. So now I have that phi, my potential functions, they all solve the Laplacian equation to satisfy continuity. So if my vector field is potential of a potential function, I have that the u and v are to have these relationships, but instead of having my automatic continuity situation is not sort of satisfied, what I now at least know is that phi, they're sometimes called, you say they're a harmonic function. Doesn't really matter what that is. The idea is that there's just nice properties we already know about what phi is, right? So it's harmonic. You also think about that this potential function solves the Laplacian, which is another very good property just because it's a nice, right, sort of helpful. There's just nice properties of this fact, where if I go to this potential function, which I can only say because I know my flow is irrotational, I get a new relationship to try to find v's and u's. And that is that at least I know that this is a harmonic function or solves the Laplacian. These are equivalent definitions, actually. So let's look at one sort of neat thing that this does, this interpretation, right? So this is this idea of a Bernoulli equation, right? The assumptions of Bernoulli's was always what? It's inviscid, that's inviscid steady. You got all these, right? All the things. But you can even get an unsteady Bernoulli equation, right? So by using vector identities, right, you can write the Navier-Stokes equations to look like this. Yes, that's right. I did it. Do you care how I got this or why you would do this in the first place? Right, this isn't a math course, so I'm trying not to do these steps for you. But importantly, maybe to motivate the idea is you have the Navier-Stokes equations or the momentum equations in terms of a symbolic representation. Right? It was written out one way. You have this property now of the velocity field that you're claiming. I'm saying it's irrotational. This term is 0. Right? So the motivation why you'd ever write this thing like this way is if I can get cross products of the velocity field in that expression, I can zero them out to make a simpler expression. That's why you would write this out, okay? That's where somebody thought about doing this. It wasn't that they were really, I don't think it was because they were that smart. The idea being is I'm investigating my assumption that I have an irrotational flow. You get this far, you say, this is a nice proof actually, right? I love this. I like this one. It's really done in classical mechanics, this idea that if you have this in your conservative forces, doesn't matter for us. So you look it up in a book that this means that all the forces are conservative, meaning you get this. Here are some definitions of phi, but you want to get further on this momentum equation. So you just write, you re-express it with vector identities, this this cross product of v star in there. And that's just using vector identities that you find, especially nowadays where somebody already discovered the vector identities for you. We don't really know because it's already seen. Okay, so I said irrotational, so I know that these now are 0. What else do we get? Okay, I won't say steady. Usually in Bernoulli's, you always said it has to be some steady function, right? 10 minutes, go a little bit over. You always said, like, Bernoulli's like, it's steady, it's inviscid, it's blah, 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 right? So now we get a little further. I'm not even going to say steady, right? Because I know that my v is a potential function, right? So plugging that in there, I now get this equals 0. You don't need to prove to me that you can swap this derivative of partial time with the gradient, but the idea of I've swapped this to pull the gradient in front of everything. But you can if everything's smooth enough. Okay, so this is the same type of thing, right? If you have like d total derivative, let's say, of like f of x plus g of x, right? You could say something like this. If you have this outside and this equaling 0, this is the conclusion you have. Well, that means that like f of x plus g of x must equal to some constant value, right? So it's sort of the same conclusion you have. It's just going to be a multivariable integration you would do. I've just integrated, right? You just integrate over the boundary of something. So this integration, we allow, though, right, even this, most general. My potential function is scalar, but it has a function of time in it as well, x, y, z, and t. So if it's inviscid or irrotational, I have this conclusion, and then you get this even time-varying part, what's called the unsteady Bernoulli's equation. It's pretty powerful, and there's some important properties of it, right? So just by integrating it out, you have now right? If I take the gradient of both these sides, I would get this expression, this being 0, because the gradient of this only is a function of time and zeroes it out. So it's sort of the same thing as like your additive constant if you integrate it out. Again, right, you're integrating both these things over the boundary. And that's important about the unsteady Bernoulli's equation is just this, that the time part so it's boundary data. The integration, so I integrate, if phi is explaining some sort of capital omega over an entire field, when I integrate over the entire domain, I now get all of the time stuff being a boundary information. So here's one example where I saw that happen. Expanding bubble problem. So this is a situation where I have some bubble in infinite space. Okay, and it's expanding equally in all directions at some radius as a function of time. That's where I have to start this problem formulation by say there's some bubble, right? Let's sort of put a little bubble like this, right? So it's an expanding bubble and maybe in a fluid medium. So even this idea that you have some sort of like gas inside bubble, this is the simplest expression you could do for this bubble liquid. Simplest type of problem you can do, right, of this expanding bubble, but still gives an interesting governing equation. But importantly, you have to posit that the boundary is just this expanding sphere. So the only thing changing as a function of time is this radius now, and you're on the hunt for R of t. Okay, so how do we get on the hunt for R of t? So first, you just go that you know that if this is irrotational inviscid, right, and that's more properties for this to obey this. So to have this be inviscid, right, you still have the situation where even though it's expanding, right, that there's no, you could calculate out this total expansion of it being irrotational. So how would we say this, right? What was it? Oh, this is irrotational because this is a divergent vector field. And the cross product with divergence is 0. So this is sort of tricky, again, because you have to get this conclusion. You don't know what the velocity field is, but by my model, right, I'm saying it's a constant expansion happening. So you say that this vector field is like, right, so this vector field is divergence, the diverging vector field. And the cross product of that is 0. I don't know. I mean, yeah. I'm sorry. So you have to say that, that it satisfies this. You have to at least get the satisfying the irrotational flow. If you have that, then you have to know that it's then this is what you're on the hunt for. You're also looking that this is modeled by some velocity potential that solves the Laplace equation. OK, so what are the boundary conditions for this? Well, I have this squared in sort of in radial coordinates, right? Here's my PDE. Right, for x, y, and then even of t, or really r and t. And what a boundary condition? Well, we have that and then let's think about these right now, right? So this boundary condition for what this this boundary condition for what this is saying as r grows away and away and away from the field, right? At the very surface, there's some radial velocity of how this is moving away. But as I go further and further out, this idea that it goes down to 0. So if I'm looking at this surface expanding, I'm looking at that radial velocity outward of the gas bubble. This is what this boundary condition is saying. Well, as I go further and further out, if it's just in a quiescent liquid, there's no actual radial velocity at all. It's gone far out enough that it's just still liquid on the outside. There's another derivative, right? So now I'm asking, OK, well then this at r, at the value of r, so here's actually r, right? This is really your r of t. Well, the derivative of phi at r is r dot, right? You can do this even by just notice that you have this being what do you have here? So now this is r dot, change it. Okay. Oh, yeah, right. So because this I'm just saying that because of the potential function's definition, right? It's the idea that, right, the gradient with r is my radial velocity, and then the gradient with phi, or the spherical coordinates, that's what they would be. So and then the radius, then the radial velocity is just this. It's dr dt. Those are those boundary conditions. Again, all I'm stating actually is that since I know it's a potential flow, since I'm saying it's an irrotational flow, I get to flat out say it must solve this equation. So I write this out. I actually do this in spherical. To do this in spherical, right, lock everything out because there's no angular velocities at all, we're going to say, and then you just apply these boundary conditions. Just apply these boundary conditions. OK. Importantly, though, now I use my unsteady Bernoulli's equation. I just plug this thing into there. I need to find out I need to find a form now of this phi to plug into there. So I don't actually solve this. I just look at this one boundary condition right here. Right? So this was equal to, right, VR. Okay, so spherical coordinates, this will look like this. Okay. And then what do you do from here? So this is just the kind of equation I have. I know what this term is. It's the VR right there. So then just looking at the boundary data, r squared again, this boundary data is what I'm trying to illustrate with this idea of if it's irrotational, I can write an unsteady Bernoulli's term where all the time variation is in this boundary integration. Boundary being the time part, the r of t is this, right? In general, it's r squared VR, but at the boundary, this is going to be r squared, and then the rt right there. And that's based on that I know this is equal to r dot. Okay, so separately then, we do our integration. We're going to integrate away to figure out what phi looks like. Almost done. So then I have this phi. Done is I've integrated out for this velocity term. I've integrated from the radius all the way out to infinity. So I go from AR all the way out to infinity. I know there's some zeroing out. Here I say that this is some gauge, but you can set that gauge equal to 0. We have this integral expression now for what phi should look like. So this phi plugged now into this expression, because there's derivatives in there with respect to r. Things cancel out because the derivative, right? Derivative with r with respect to an integral derivative cancel each other out. But if I have two of them, they pop back in there. Yada, yada, yada. So again, this going into here, realizing that only r terms are left over, we also are going to kill off the gravity because it's equal in all directions. That's the final form I want. And then you get this and then you have the ODE that governs this expanding bubble in gas. It's only going to be true for actually short amounts of times, but it's just amazing that you could just do it from just plugging it into some unsteady Bernoulli equation. All I knew to get this equation was I have it be irrotational because it's a divergent vector, because the velocity field comes from a divergence. So I know that my potential must solve this equation, and then there are some boundary conditions. One of the boundary conditions being that the dFr is really the r star, and then the form of this spherical one having this in there. Right? And via integration then of what the phi is, okay, you end up then plugging this into your unstable Bernoulli equations and get this equation An ODE is just for looking for R of t because there's a lot of symmetry that happened in this problem. But from just looking at these flows in terms of potential functions instead of stream functions, we get simpler methods to write out ODEs that govern the flow systems. That's the main point about stream functions and potential functions, I would say, is it's a slightly easier calculus to get what governs the dynamics. And I gave you the example of having an asymptotic suction flow where, again, I just had this big one, and you had this porous thing, and things kill off in there. But I had a different general equation that I can just plug things into, and then I get the solutions even from there. This one I can't write out a solution to because it's wholly nonlinear, but I at least can model now in a computer how this expanding gas will be, right? And I have now this pressure difference in there. So I now need to assign some pressure as a function of R for this to be a well-defined ODE. This is a P as a function of R. So if you give me some pressure distribution or pressure variation, like a sinusoidal pressure variation of a wobbly bubble, you can then numerically solve that. If you have some sort of condensing pressure field or expanding, you have to plug in some sort of functional form for this pressure as a function of R, and then this ODE is solvable. You just need to give it some initial conditions to integrate them forward. OK, that was two examples of using stream functions and potential functions. Hopefully that seems slightly easier. If nothing's seeming easier in the class, keep working on the homeworks. Hopefully I'll help you off. Really, this stuff I just think about it where it's just like it's almost like miraculous that this stuff really does work.
Sway, my God, don't sway. My God, don't sway. My God, sway. My God, don't sway. Something real good. Something you could look forward to. Well, don't you cry now. Keep going. Just trust. And always remember, it's already done.
I'm looking for a miracle. I'm looking for a miracle. Deep in my heart. Looking for a miracle. I'm looking for a miracle. So deep in my heart. Miracle. Oh,
miracle. Well, if you haven't noticed, look around, baby. You're the mirror. That's right. You. 100% bona fide grade A miracle.
looking for deep in my heart. One day I'll realize I'm a miracle.
What you're gonna do with that miracle is what we want to know. That's up to you.
We will rise.